All this is Derek in section 8.2, complex fractions. And so what a complex fraction is when there is a fraction within a fraction. And so this section is about how to simplify under those circumstances. And we're going to look at two styles. We're going to look at where it's just a fraction over a fraction, which are actually, we already know how to do them. And then we're going to look at a version where we have addition and subtraction going on. We'll see that in a couple examples. So for this first problem, this says 4/9 divided by 5/18. So let me rewrite what I just said. 4/9 divided by 5/18. So those are the exact same problem. If it's written this way, it looks scary. If it's written this way, it looks like something we've done. We just take the reciprocal of the second one and then factor cancel and then multiply if we have to. So here we go, 4/9 times 18 over 5. We can, right here, let's go 9 goes into 9 once, 9 goes into 18 twice. Reduce out that common factor of 9. 4 times 2 is 8. 1 times 5 is 5. So these are really problems we have already done in disguise. So this one right here, 15 a to the 8th over 14b to the 9th. I'm going to bring this up. Think of that as being 33 over 7. So I'm going to flip it and rewrite it as a multiply. And let me do a thing down here to explain that. So if you think of having something of this form, a over b divided by c over d, it's going to come out a over b divided by c over d, and then you're going to do that reciprocal, and you're going to have a over b times d over c every time. And so if you see what I'm doing here, I'm bringing this up, and then I'm just sort of flipping it in my head so that I don't have to write this step as the problems get longer. So that is where it's going to land. So now that I've done that, let's go ahead and go 7 goes into 14. 7 goes in 7 once, 7 goes to 14 twice. And then the 15 and the 33, those actually common 3. So 3 goes into 15 5 times. 3 goes into 33 11 times. So in terms of the numbers, we got 5 times 1 is 5. And 2 times 11 is 22. A to the 8th right there, a to the 6th there. So that's going to leave me a squared up top. And b to the 4th up top, b to the 9th down below. So if I cancel out 4 of them, I will still have 5 left in my denominator. So b to the 5th. So this one's the same thing. It's a single fraction divided by a single fraction. So I can just rewrite this as x squared minus 9, x squared minus 5x plus 4. Instead of stopping off at divided by, again, I'm just going to use this idea that whatever this fraction is, it's going to come up and flip over. So that's going to be x minus 4 up top, and then x plus 3 down below. Once I got that, now I can just go ahead and factor and cancel. So x plus 3 and x minus 3 for the difference of squares. Multiplies to 4, adds negative 5, so x minus 1, x minus 4. That'll be times x minus 4, and then that x plus 3 down below. So plus 3's cancel, minus 4's cancel. So the only thing left is x minus 3 over x minus 1. Okay, for this next round, we are looking at complex fractions that involve addition or subtraction. So this thing where we just bring it up and flip is no longer going to be, it still works, but we'd have to add and subtract first in those parentheses and then do the multiplication division. And the order of operations on that is really messy, and it's not a good way to solve. So there are two ways to do these. What I have here in the directions is the one that I think is the better one. It is a little bit harder to get your brain around to learn how to do it, but once you do, the math is a lot easier. I wrote this out on a separate piece of paper, and I'm going to do one of these out the way that your brain is going to tell you to do it in an attempt to convince you that your brain is leading you astray, and this is the hard way. So if we do this in the manner that would be intuitive, we would put these together, we would put these together, and then do what we just did on those last problems. So doing that, we're going to have a 2 over 2 right here. We would need 5 over 5 right there. And then that's going to get this up to 10th, so I can put that together. 60 and 10, my LCD would be 30. So this needs 3s, and this needs 5s. So that will make 5/10 minus 2/10 over 5/30 plus 3/30. And then collecting there, I'm going to have 5 minus 2, so that would be 3/10. And then 5/30 plus 3/30, that would be 8/30. And then rewrite that 3/10 divided by 8/30. That's what we were just doing. And then we do our reciprocal, so 3 over 10 times 30 over 8. And it looks like 10 goes into 10 once, 10 goes into that 3 times. And so hopefully this comes out to 9/8, which it does. Okay, so that was, oops, and then I wrote 9/9, so 9/8. So that was the long, terrible, hard way to do the problem, and that's the way that you're going to be inclined to do these, and you don't want to do that. Here's what you want to do. Instead, you want to find the LCD for all the fractions. So notice when I did this, I only worried about getting the numerators and the denominators together. Here I want to look at 2, 5, 6, and 10 and say LCD is 30, right? So LCD is going to equal 30 in this case. And then I want to multiply the numerator and denominator of the complex fraction by the LCD. Let me show you what I mean by that. So I'm going to write this a little bit bigger. So we want to multiply everything by the LCD. So this is going to be 30 times that half, 30 times the fifth, 30 times the sixth, and 30 times the 10th. And if it helps, you can think of those as all over 1. And the reason we're using the LCD is because what it's about to do is clear all these fractions. And because I am multiplying every single term by 30, it's cool. I can't pick and choose, and I have to multiply everything by the same thing, but as long as I do that, that is okay math. So this will be 30 over 2, that is 15. This will be 30 over 5, that is 6. This will be 30 over 6, that is 5. This will be 30 over 10, and that is 3. 15 minus 6 is 9, 5 and 3 makes 8. So same thing I got over here with a lot more suffering I can get here. Also, I mean, when I'm doing this for me, right, I would have gone 30, 30, and I'm not writing all this stuff. I'm just going 2 into that 15, that would make my 6, 5, 3. So this step was just really to make it large enough for you to see and hopefully that you could follow my canceling. So this is a much easier way to solve these. So for this next one, we have a whole number, -4 plus 2 over x, and then same thing, 7 plus 3 over x. So for an LCD, all we have is just that x. And so here we'll go x times -4, cool, -4x. Here, this would be 2x over x, so those would cancel, and we would just have plus 2. So it clears the fraction, and that's the goal. We're trying to get the fractions out of our fractions. Doing the same thing down here, x over x, I should have written that at the same time. X times 7 would be 7x, and again, this would be 3x over x, so those x's would cancel, leaving a 3. Nothing factors, they're not the same, so I can't reduce. And that's the end of that problem. For 6, here, we're going to use x squared, and this is going to go x squared times 1 is x squared, and then here, let me write this out, x squared over x, in case people are having a hard time with seeing the canceling. So this is x squared minus 25, x squared over x squared. So I'm just showing this x squared multiplied to the 1, to the 5x, to the 1, and to the 25. And now we can see, hopefully, x squared plus 5x squared over x. That's where I'm getting that canceling here. I just go 2 up, 1 down, so that would leave me a 5x. But that's kind of what I'm envisioning in my head. Likewise here, x squared, and then I'm just seeing this as canceling those two because of right there. This is a very suspicious answer with all those things at factors, so I bet it's going to reduce. We'll come down here. We take an x out of the numerator, so that's x plus 5. And then x plus 5, x minus 5 on the denominator. And we cancel our plus 5s. Okay, this example we got some negative exponents. So let me remind you that this would go 1, and then negative 9x to the negative 2 is the same thing as negative 9 over x squared. Here, this is 1 plus x to the negative 1, so that's the same as plus 1 over x. And here, this x to the negative 2, so that's minus 6, and then x squared. So I can rewrite the problem that way, and then that will help me see that my common denominator is x squared. Or if I want to be super clever and notice that what I need to do is get rid of all these negative exponents, I could just do it right here and think of it as, just adding the exponents. So up here, this would be x squared, and then negative 2 plus 2 would be x to the 0, so that's 1. 1 times negative 9. Here, x squared times 1, negative 1 plus 2 would be plus x. Negative 2 plus 2, there's that 0 making a 1 again. So that would be one way of looking at it. I think probably most people will be more comfortable with the canceling version, so here's that. X squared times 1 is x squared. Here, the x squareds cancel, leaving the 9. X squared times 1, x squared up, x down below, that is x, and then there they would cancel, leaving a 6. So 2 ways of looking at it. We end up at the exact same spot, and either way we do need to factor, so x plus 3 and x minus 3. And let's see, multiplies to negative 6 and adds to be positive 1 will be x plus 3 and x minus 2. And we got plus 3's canceling, so that would be our solution. So then this last one, we're going to multiply everything by x plus 4. So here we'll think 2 times x plus 4 minus 9, and then the x plus 4's cancel. Here we would have x plus 4's canceling, so we would just have that 7x, but then times negative 6, and that's also times x plus 4, because it's like we're distributing this to both of those. And then collecting and simplifying, we're going to get 2x plus 8 minus 9 over 7x minus 6x minus 24. So it looks like we end up 2x minus 1 over x and then minus 24.